everybody. My purpose today will be to speak about TNAs conducted in Inria at Inria in Rennes. So far conducted 3 TNAs. Let me introduce the 3 TNAs. So the first one was Ergo. It was conducted by Pascal Madeleine of Aalborg University. It was on ergonomics in virtual environments. The second one was conducted by Alexandra Kovaci from Transylvania University of Brasov, and it's on VR accelerator for learning basketball throws. And the last one was conducted by Grani Francesco from Aalborg University in Copenhagen, and it asked surrounded by contact, spatialization of multiple contact zones in immersive space. So the 3, as you can see, are related to VR. It's normal because our platform is a VR platform. So I will try to be quick and to summarize and to give up the results that were shown during these experiments. So let's go with Virgo. It's ergonomics in virtual environments. So the idea is to try to assess the functional realism of simulators, VR simulators, for ergonomics. So let's, here you can, yes, you see what I show. We try to have a VR simulation with data logging, with motion capture and electromyographics. Motion is for motion capture, is based on markers in an immersive room to capture the motion, and the colleagues from Aalborg University brought EMG to record the muscle activity. So the idea is to go to an analysis both of the motion and the EMG signals, and to try to put ergonomic diagnosis in order either to improve the workstation design. So here it's a mock-up of the workstation, and of course trying also to improve a gesture of the user during the operation. So to design the experimentation, we tried to define a hole box that you have here with 6 holes or 2 holes with objects that are called fitters, so they go inside the holes, or non-fitters, they cannot go inside the holes. And here we have the 6 fitters complexity, and here the 2 fitters complexity. So to do that, we have to design the mock-up for ergonomic purpose, to take into account technical limitation. Let's, for example, interaction possibilities. You know that in VR interaction, we wish interaction to be natural, but it's not always possible to have a natural interaction. And so it was the beginning point. To more specify the experimentation, we had 12 parts for each trial, and subject has to place 6 fitters in the corresponding holes or to a disposal zone that we cannot see here. It just up the mock-up. The timing regime we defined was as fast as possible, so do the manipulation as fast as you can, or time managed, let's say 10 seconds per part. And complexity, as already said, that it was 2 or 6 holes. Here we have a view in virtual. As you can see here, the mock-up is digital in the immersive room. Here we have the user with EMGs, and we see the ropes here. And here we have a haptic device, so a real haptic device. So the idea was to compare three interaction types. The real one, the mock-up was also a real one. This one is digital on the picture, but it was also a real one. We have the virtual without feedback, force feedback, we call it virtual, and virtual with force feedback with this haptic device. And here we have, of course, the configuration virtual plus force feedback. The measurements, due to motion capture, we can measure segment orientation and build a RULA score, that is the well-known postural criteria in ergonomics. We measure, due to EMGs, the average muscle activations, a rate of perceived exertion and presence and discomfort was built on a questionnaire. So to build the mockup and the digital mockup, we had the same idea. Here you have in real, here you have in virtual, here in virtual plus haptic. The idea was to have a mockup that was flexible, practical, mountable and exportable. So the idea was to design the mockup digitally, so to build a digital mockup and to go to STL and assembly plans and end nodes for building the real setup. And here you have the virtual part. You have to get this geometrical definition and to use a physics engine to see with collision detection to compute if the fitters fits in the holes or not, and you have to have a rendering engine. So all was done in our framework in the Inria room. So during the stay of the colleagues, they stayed 10 days plus 1 weekend, but of course it was free during the weekend. We had 10 subjects, VR novice, so not used to use virtual environment. I have no, I think I lost the age, the size and the weight, so no matter for the explanation, and they had no reported musculoskeletal disorder during the last 6 months. All but 3 were right-handed. So once again, you have a picture of what we did. So here I have a movie. Perhaps there is some sound because of a condition of recording in the room, so don't pay attention to the sound. And here we are in virtual, of course, with EMG and with, you will see the experience. So this is a fitter, you put it in the hole, and of course you have a non-fitter, so it was put on the disposal. So let's have a very small discussion. Accessibility was more difficult in virtual environments than in real environments, and more difficult in virtual environment with force feedback than in real environment, and in virtual environment with force feedback than in virtual environment. So real was easier for the accessibility point of view. Virtual was more difficult, and virtual with force feedback was even more difficult. Well, same thing on, so it was more on accessibility and positioning. The second thing was placing the fitters was more difficult with the same conclusion, more easier in real environment and more difficult in virtual environment with force feedback. And also we noticed that motion tended to be less natural in the same with the same conclusion. Virtual environment and real environment are closer than virtual environment with force feedback and real environment. It's certainly due to mechanical limitation of the haptic device we had. It's a Virtuos 6D from Aption. Clearly, rotation is quite difficult to obtain with this kind of devices, but it's known in haptic rendering. So the second one was on VR for learning basketball throws. So the idea is to implement a free throw simulator. So of course, when designing, so here on the right you have a first-person view of the simulator. So the guy is throwing his ball and is in immersive room. With here the red point is a motion capture camera, for example. So of course we try to develop, and Alexandra tried to develop a user-friendly interface, possibility to change the point of view or something like that. Modular platform to add new skills easily, and trying to build a learning platform for people. The idea was to test and to the increasing of the quality and the speed of learning for a free throw in baskets, and trying to develop motor skills to the user. So she has a target application that is a home training system based on a small video projector or a wide screen with low-cost devices. And the question also she had was to say, oh, in this type of system, we will not be able to do one-to-one scale immersion. Of course, Inertia allows that on this kind of experiment, but at home it will be difficult. So the question were, is one-one scale system with first-person view, so people inside the environment, and comparable to a real basketball stadium? So can we use VR for free throws? What are the difference between first person and third person view? So first you are inside the immersive room and inside the environment. Third person, you look at it from outside. So maybe it's more convenient for home training systems, for example. And what are the consequences of adding information about the optimal trajectory of the ball? So the free throw is far from the, I don't know, from the target, and maybe you can add visual clues helping you to better send your ball. And all that was tested in random order. So the protocol was the adaptation of a publication from Alexandra to Inertia to one-on-one scale projection with first-person view, and with a real ball tracked by an accurate motion capture system. So it was quite funny to do that, because we had to track the ball, a real one, and to bind it with a rope and to avoid the ball going to the screen. So it was quite mechanically interesting to find this kind of thing. In this context, she claims we are in the highest quality for both motion capture and display because of the virtual environment and the immersive room and the motion capture that is Vicon 1. And so we can analyze the potential performance of the environment, virtual environment, compared to the virtual world. It was based on a Unity project for a software point of view, because it's quite easy to develop with Unity for this kind of applications. Real experiments in real stadiums were performed with the same subject, and the performance measurement consisted in success ratio, initial and final ball velocity, distance to the ring to the target when missing, and joint trajectories, so motion of the capture of the subjects. And as I said, all the experiments were done also in virtual for all the subjects. For question 2, regarding first third-person view. So third-person view is a first step to home application where it is impossible to have one-to-one scale environment. It is also impossible to have a vacant system and of course an inertia room at home or in small clubs. So the idea was trying to move the viewpoint, and here it's moved 3 meters backward of the actual position in space. The tracking of the ball was also performed by the Vicon system, and the display was in real time. The third question was about the learning accelerator and adding visual clues to help the user to reach the target with the ball. So it was performed in third-person view. Additional feedback, it is mainly visual clues, as I said. It was built upon a series of circles in the air in which the ball should go to ensure success of the throw. And of course, the user can target the closest circle, which is much easier to target the basketball ring. It was built a physical model of the ball with the optimal ball initial velocity vector to build the series of circles, and optimal initial ball parameters were analyzed according to pre-experimental in real stadium for the subjects. So, of course, as usual in VR, it was a questionnaire of presence, and that was adapted to this specific protocol. And here you have the third-person view with visual clues, and you can see the visual clues here. Of course, on a flat screen you can not see the 3D effect, but in Immersia you had a 3D effect, of course. With respect to success ratio, of course standard deviation are on this picture are large, so it's difficult to conclude. And it's also a group of all the subjects that is analyzed here in this first try to analyze the things. So nevertheless, there is no significant difference between the group. Performance between real and virtual are quite more or less similar, and first or third person do not seem to have effect on success ratio. Same thing on the average distance between the final ball position and the middle of the ring. No significant difference between real and virtual, and no significant difference between first and third person view. The smaller standard there is a smaller standard deviation, so those things are more reliable, and there is a slightly smaller distance to the basketball ring when using the accelerator due to the circles that are clues, visual clues. So as a partial conclusion, Alexandra was very happy to do that because it was a multidisciplinary work. She comes from sports science and biomechanics and had the opportunity to deal with computer science and virtual reality. So she was very happy because Immersia was and Visionair helping her to come to Immersia was a unique chance to test this kind of things. And it was very well adapted because for basketball you need large spaces, high speeds, high accuracy. So the technical facility gives us the possibility to evaluate if immersive environments are promising means to improve physical performance. So it has been demonstrated in the literature that it clearly improves the motivation, but it's still difficult to demonstrate if it improves the physical skills and the learning process. So the next step of the process for Alexandra Kovaci is to try to analyze more clearly how such a VR approach improves the learning process and could be adapted to low-cost systems. So last but not least, it's on contact sound in spatialized immersive space. So the idea was to test the importance of spatialized audio in a VR walking experience. And it was built an interactive audiovisual environment where the user walks around in presence of sounding object. As you know, Immersia is 10 meters long, so it was designed at the beginning to allow physical motion within the environment. So we have 10 meters by 3 meters for the ground, and of course you can walk physically on this place. So the interaction with the environment was tested in different conditions. Sound rendered by binaural techniques, sound rendered by binaural but affected by a roto translation. Don't ask me what it is. I don't know exactly. I think the source is not where we think she is. It is. And sound is rendered by a stereo technique, not a standard one, an improved one, but not standard stereo technique, an improved one, but a stereo technique. I think it's 2.0, but I'm not sure. And the idea was also to test the degree of immersion that the user can achieve in the different conditions and test the difference that can be identified by the user between those different kinds of auditory feedback. So volunteers participated to user experience evaluation. I don't know exactly how many volunteers. I think they were quite numerous, let's say around 20, but I have not the figure. And the task was to walk inside the natural environment, so nature, built with Unity 3D, and the idea was to try to follow a precise path. The object contained some punctual audio objects, a frog, a goose, a bird, I think a snake also, and some else, and a specific MaxMSP, so that is a sound software, was designed to perform a real-time rendering of different techniques. So each work was performed twice by the volunteer user with two different audio scenarios to be compared at each time. So good binaural, so the best quality it was possible to achieve. Bad binaural, so the auditory word was rotated by 90 degrees and shifted by 5 meters. So incoherency because between the sound and the visual immersion, and a good stereo, so but with ambisonic down mix, so not binaural, a good stereo located at the good point, but not the same audio rendering. Of course, what interested them was also the high-resolution stereoscopic immersion room in Immersia, and the 3D, so the 360 tracking system with, here we used or RT infrared cameras. We have IRTs, 16 IRTs in the inertial room, and for basketball we borrowed Vicon because they are quicker than IRT for the ball capture. So we have to borrow some Vicon camera. So of course it was a questionnaire for the subjective evaluation, and the idea was to say, to ask about the general appreciation and the coherence of the auditory feedback we have here, and comparing two scenarios. It was asked what was the best in terms of immersion and auditory rendering. Open questions were also led to the user if they want to answer. So the first results are showing, and I think it was assumed, that rich auditory rendering is more appreciated in terms of immersion. All the subjects expressed a strong preference for the good auditory rendering technique. Good is binaural and stereo, but not with no disturbance, with a good localization of the sound source. The question with good binaural rendering with respect to rich stereo rendering was not completely closed, and I think there is no work to do in that direction. And the binaural rendering is preferred, but no, I think that they are not sure of the difference they obtained. Of course, they want to use their audio rendering software tool to try to carry on other works in spatialized auditory feedback in VR.
George, it was about the number of the sensors of EMG. We use it on behalf of the people who was involved in this experience about
yes.
How many sensors and which position on behalf of the people?
I don't know. I think they were quite numerous. I remember maybe 18 channel EMG entry, something like that. It was quite, can we see that on the pictures? Here we have an idea of the, dorsal, arm, if I remember well. It was equipped on one arm on the deltoids, I think. And so they brought the material. We had just to develop an Arduino device to synchronize the start point of the virtual experiment and the start point of the EMG recording, and to be able to synchronize after.
Mm-hmm. And George, I'm asking this question because we also realized some experience here in the frame of Master 2 research this year. And the next question is about the noise. So which kind of technique did you use in order to avoid the noise in the recording of the signals? Do you know?
You can send me a mail and I will ask him
okay, George,
more precise.
Uh-huh.
We have a publication at CogInfocom, but we did not show up this part.
You mentioned that you used collision detection for the filters entering in the hole. How did you manage this?
Yeah. So in this, we used bullet, I think. So I don't like it very much because it's not so mechanical. But as you know, it's quite difficult to this kind of thing. So we used Bullet. We wanted to use other things, but they were not completely available in the new version of our inertia room. So I am trying to go further in this direction and to use, for example, IPSI, that is the CEA software that you can use with Action device. So I'm trying to have one engineer working on that, but I think it's not going so quick for the moment. But this is an idea, and maybe it was using Bullet but done on purpose, more or less. For example, with respect to convex form, if I remember well, Bullet needs convex form, so the graphical forms are the real one, and the mechanical form are other form in the simulation.
Okay, and do you think that it played a role in the results that you are obtaining? I mean, if you are changing bullets for another system of rendering the collision or the link between the parts going through the hole, do you think that it will change maybe the order of the answers?
The order of the answers, no. The quality of the rendering, certainly. I think clearly, very intuitively, it's easier in real, clearly, because we use the hand. In virtual, it's quite easy because we have a fly stick. So more or less, we use the hand and we can take the same position. And in virtual with haptic, of course, you have to manage the device. So I think the order will not change so much. Concerning the haptic feeling with physics engine, mainly it's more or less with the fly stick. You cannot see the difference between the physics engine. Once you have the good joint model, there's no problem, I think. With haptic, certainly we can change the feedback. And we tried to answer to this question because we had an internship on this subject on analysis graphic with all distortion, so physics model with respect to visual model during this spring, and so the guy was not good, so we have no answer. But the question is a good question.
Just a question on your second TNA that you described about the basketball simulation training. Did you try only from the same position, the free throw, or you also tried different positions to see how the distance is affecting the results?
I'm not completely sure, but I think the context of free throw is more or less fixed, because I think in basketball, when for a free throw, you have to be standing in your ring and to try to. So I think it was just that for the moment. So it was fixed for the geometry.